All right, here we're going to do problem 674. This is actually a relatively easy problem. The hardest thing about this is trying to visualize what is the beam and then get the loading onto the beam. Basically you're designing this boat trailer, which is idealized as a beam. It has this cross-section. This is kind of a tricky cross-section. Actually, you know what I'll probably do here? I might pause here and show you how to use a spreadsheet to kind of compute these composite sections. Although this one's not too bad. I could probably... No, actually there's a shortcut. I'll do it. I'll do it a simple way. Maybe I'll do a spreadsheet in another video. And you just have to find the maximum stress in this box beam, okay? So the boat is resting at point A, and it's basically pinned at B. So you can imagine that really there's well, let's assume that they're downward. They'll probably have to flip, right? This one will probably have to flip. Well, it depends on where it is, but this one might have to flip, so let's assume it's upward. So these are going to be the forces that are acting on this beam, right? This is the beam we're trying to design. This section here. A to C. This boat really doesn't matter, other than the fact we have to use equilibrium equations on the boat to get the reaction forces. Okay? All right. So this one's got a little bit of like a step zero. We're going to have to do equilibrium on the boat to get the reaction forces, the force at B and the force at A that act on the beam. Okay? And then we'll go through the usual steps. Then we'll get the bending moment diagram in the beam AC, and then we'll have to get the area properties, the eyes in the center of the neutral axis location, the centroid, and then finally put that into the flexure formula. Okay, right, the area properties, this is where we want to get I and the maximum C. Okay? This is symmetric, so it'll be the same C either way. All right, so let's do the step zero. So if we look at the boat, let me try to draw a boat. Here's the boat. So acting on the boat, we've got this force A. And since I drew this going upward, this would actually be a downward force at B. Again, it doesn't really matter which way you draw it. These I've drawn here, these are the forces on the beam. So the forces acting on the boat are equal and opposite. And, if B turns out to be in compression, obviously it'll just flip signs. And then here's G. So the boat weighs 2,300 pounds. This distance here is 4 feet, and this distance here is 4 feet as well. Right? It's going, no, it's 5 feet. I'm sorry. It's 5 feet. Because from here to here is 5 feet. And then we got 1 foot between the wheel and the center of gravity. All right. So we know that FA has to equal the 2,300 plus FB. And then let's do sum of moments around A to get FB. So we do sum of moments around A, and that equals the weight of the boat is a negative moment, 2,300. Its moment arm is 4. And then the FB is also going to give me a negative moment, minus FB, and its moment arm is 9. And that has to go to 0. So that gives me that FB, and in fact I did get the wrong sign on it, FB is going to be equal to minus 2300 times 4 over 9, which is 1022 pounds. Okay, and a minus. So actually, it's actually acting downward. Okay, I'm sorry. This is actually acting upward. Okay. All right, and then that tells me that the FA, putting this into here, gives me 1278 pounds. Positive, so it's acting up. So actually, the free body diagram on the beam now looks as follows. Okay, so here's the actual beam that we're designing. Okay, so we have a unknown reaction force at the trailer hitch, point C. We'll call this force C. Then we've got this known force acting at B, right? Which you already figured out is actually acting downward. Right? It's actually right. It's actually the upward force on the boat, so it's a compressional force. So it's about here. It acts downward. That's at B, and that has a value of 1022 pounds. That's known. We also have at A, another downward force from the boat. That's 1278 pounds acting downward. That's at point A. And then right here at point D, where the wheel force acts up, we have a supporting force of the wheel, FD. And I'll draw that up as well. So now I need to get FD and FC on this beam. So this is actually the beam we're going to analyze. This step 0, so we're actually now starting to do step 1. This step 0 is just to get these two reaction forces of the boat acting on to the trailer. Okay? All right, and we'll put some dimensions on here. This is 4 feet. This is 1 foot. This is, wait, what am I doing? I'm sorry, I didn't draw this very well. D is back here. D is, 3 feet from A. And then we go another 6 feet from D to B. So I didn't really draw this to scale. D's actually should be back farther. And then this is another 4 feet from B to C. Okay, so that's a little sloppy, but those are the forces. That's the distances. Okay, so we need to get FD and FC. So again, equilibrium. Let me get another piece of paper, I guess. Okay, so sum of forces in the y direction, that gives me FC plus FD has to equal the 1278 plus 1022 pounds. That's of course going to equal that's 2300. It's the total weight of the boat, right? They have to equal the total weight of the boat, or it better be, right? Otherwise I screwed up here. And then let's do sum of moments around. Let's do around point C. So we drop out the C and we can get an equation that just involves D. Of course, you can pick any one that you want. So if we pick it around point C, all right, this force A is a positive moment, 1278, and its moment arm is 13 feet. FD produces a negative moment around C, and its moment arm is 10 feet. The 1022 produces a positive moment. 1022, and its moment arm is 4 feet, and that's all we got. This has to go to 0, so this gives me that the force at D is 4 times 1022 plus 13 times 1078 divided by 10, which is equal to 2070 pounds. Okay? And now, knowing that, we can get that F at C is going to equal 2300 minus 2070, and that's just going to be 230 pounds. Okay? So now if we draw the forces on the beam, try to draw a little more to scale this time. We've got A, and then we go to D, and then we go out to another 5 feet to B, and then out to C. And we have $12.78 at A. We have upwards force at D of 2,070. These are all pounds. At B, I have another downward force of 1022 pounds. And then at C, we have upward force of 230 pounds. Okay? All right, so now we need to compute the bending moment diagram. This is nice. It's got some point loads, so we can actually kind of do this graphically, I guess. Again, the moments have to vanish at the ends. There's nothing there that it's not built in on either side, and there's no externally applied moment. We're assuming the trailer hitch is pinned, right? So we know that the moment has to vanish at both ends. Let's draw the... Okay, so here's point C, here's B, here's D, and here's A. So this is X, and this is the moment. All right. Now, if you think about it, let's start going from the left-hand side. So if we draw a section through here, right? We draw this cross-section. Then it'll have a bending moment, the internal bending moment acts clockwise because it's a negative face. And so this distance here is the length, the total length, which is, what is the total length? 13 minus x, right? And so you can see that actually this is going to produce a positive moment, right? This one is a negative moment, a positive moment. So this will actually produce a positive moment. It starts here at 0. This is point C. And it's going to go up. Maybe I'll do it in pencil so I don't screw up too much. I'll try to use a ruler. I don't usually do graphical approach, but I'm going to try to be a little more graphical on this one, okay? So it'll go up from point C. Right? All these point load, any moment that arises from a point force is going to have a linear shape to it. And it's going to obviously apply over the entire beam. And it's going to have a slope of Wait, no, wait, what am I doing? Is it going to be a positive or minus? The slope's 230. But yeah, the slope is a minus 230. Yeah, I'm sorry. Right, which is what I've drawn here. So it has to be increasing, right? So it gets maximum at this point, right? Okay. Then once we, all these sections will be the same, right? It's the same free body diagram until we get past, let's do another color, this point, right? Where we have this free body diagram. Here's the internal moment at this point. So we still have, this slope here, which is the moment caused by this 230, but now we're going to have an additional moment that's being caused by this 1022, and its moment arm is this distance here, which is going to be the distance to this point, which is 9 feet minus x, right? That's 9 feet minus x, so that's the moment arm. All right? So it's going to have a slope of, it's actually going to be a negative moment. Why is it a negative moment? This is actually going to be now I'm just talking about the effect, the moment due to this 1022, like if we just consider superposition. This is producing a negative moment around here, so that means actually the internal reaction moment has to flip the other way to balance that out. So it's going to be a negative moment, so it's going to be going down, and its slope is going to be the 1022. So I actually should have drawn this a lot less, because 230, I'm going to try to draw it to scale a little bit. Let's see if I can try to draw it to scale. So let's redraw this one. Because I'm going to have some slopes that go up to 2,000. So if 2,000 is kind of my max slope, that would be about 1,000. So yeah, this would be about, well, I'll exaggerate a little bit. Let's say that's the slope that I get. That's the minus 230. All right. So added on to that, I'm going to get a slope here from this one. Starts at 0 here, goes that way. That's going to have a slope of 1022, right? And then at this point, we do the same argument. We move sections over here. It's all the same. These two add together. And then we get to this point, and then the moment has to take into account this one, which is give me a positive moment, but its slope is going to be 2,000, so it's going to be like double that slope. So it's roughly something that looks like this. Actually, that's actually a negative number. That's a positive number, right? Might be hard for you to see. And so you have to consider these things actually added up, right? So if we draw the, let me draw the total one in blue. We haven't used blue in a while. So from, and this is point B, this is point D, and this is point A. So from C to B, we just see, oops, right? That becomes the diagram, the moment diagram. Just has that small slope of the 230. Then once you get to point B, we have to subtract off the contribution from the 1022 force. So that's going to be a moment that we'll drop over that. It's just going to follow this line. So I'm trying to draw a parallel line to that until we get to point D. So it looks like we should in fact get a sign change on the moment, and then Wait, am I doing this right? Yeah, it'll actually be, it's not going to be parallel, it's actually going to be like a bisector, right? It's actually kind of like a bisector. So actually going to go like this. So forget this line. And then it's going to go up with a slope of, so this one, I'm screwing this up. So this slope here, the actual one, this slope here is going to be the minus 230. This slope here of the resultant curve is going to be the minus 230 plus the 1022. So that is going to be a slope of 792. All right, and then when we get to this point, it's going to be the 792 minus 2070. So that gives me a minus 1278. So this is going to go from this point up something like this. Well, and then I know it goes to 0, right? It has to go to 0. And this one's going to have a slope of minus 1278. So the total bending moment diagram looks something like this. Right? Maybe I should draw a little bigger. Let me just redraw it. Well, that's good enough. We'll just leave it like that. You get the idea. So I got 2 points here that might be maximal. This one or that one. Okay? Those are the points of interest. So we should probably figure this out. This bending moment here is going to be the 230 because it goes at that slope on this distance, and that distance between B and C is 4 feet. So this is going to be 230 times 4. So this is going to have a positive bending moment of 920. Now we're talking about pound-feet here, okay? So we did all the lengths of feet. Now this one, let's see if I can do this correctly. This is going to go at this slope of 1278. It starts at 0, and this distance is 3 feet. So this moment here should be the 1278 3 times. So this is actually going to be the greater one, and it kind of looks that way from drawing it. A minus 3834 pound-feet. Okay? So this point D is actually going to have the maximum bending moment. Okay? That's what we have to design to. All right? So again, like I said, the graphical approach is nice. I think it was good back in days where people didn't have such fancy calculators or whatever, and then they were quite adept at doing things graphically. I think these days, you know, the direct computation approach is fine. I think before you start to do the graphical approach, you really have to understand how to draw the free body diagrams, because there's lots of sort of assumptions or shortcuts I'm taking in here. If you follow it and you're comfortable doing the graphical approach, so be it. No problems. But if not, go back and write the equations and do the same process that we've done in the prior examples. You should get the same numbers, okay? But from here, you're going to see that point D is the critical point. That's where the maximum stress is going to occur, because that's where the maximum bending stress is going to occur. The bending moment, excuse me. All right. So that's step 2. Now that's step 1. Now we have to do the cross-sectional area ones. So let's compute the cross-sectional area. So this is step 2. We have to get the area properties. Actually, this one isn't so bad, even though it looks like it's kind of complicated. So you have this open box shape. All right, and this dimension here is, the outer dimension is 1.75. This is all in inches. This inner dimension is 1.5. This overall dimension is 3 inches, and this inner dimension here is 1.75 as well. Okay, so you could break this up into 4 regions, if you will. You could consider the top, the bottom, and then the 2 sides, and do a composite section like that. Since it's symmetric, this one's actually quite easy. We can get the eye just as we would when we consider like a hollow tube. So we can get the eye of the box beam as if it were solid. A solid 1.75 by 3 inches. And we could subtract off of that the eye of the intersection. And the intersection is 1.5 by 1.75. Now, since both of these sections, right, have the same center point, I don't have to do parallel axis there, right? This cross section here, the whole, has its neutral axis, right? If it were an actual physical element, coincident with the neutral axis of the outer box, and that's going to be coincident with the neutral axis of this one. If this had been skewed somehow, so it wasn't centered, you would then have to do parallel axis to shift the shape and subtract it off. So we just need to subtract this eye off of this eye, and that'll give me the total eye. Okay? I'll try to do a video where I get a more complicated. Maybe I'll do like an L shape or a C channel or a Z channel and try to get the geometric properties off of a more complicated shape using a spreadsheet. But for now, we'll just do this because this is pretty easy. So the eye of this one is going to be 1/12 base times height. The base is 1.75. The height is 3. We're going to cube that. And we're going to subtract off of that this eye, which is base 1.5 times the height 1.75 cubed. Now this is all inches, so this is going to give me a result in inch to the 4th, right? So this is I. So this now becomes so this becomes 3.94 inches to the 4th minus 0.670 inches to the 4th. And so that equals 3.27 inches to the 4th. That's I. The neutral axis is going to pass right through the center. So that means the C to this outer fiber is 1.5 inches, and then the C distance to this bottom fiber is equal 1.5 inches. Okay? So we have so you have the same C in both directions. Okay? All right. So let's finish up the problem. We're almost there. We need to now do the third step. We have to find the stress. So the stress max, this is going to occur at point D, where we have that maximum bending moment, which is the, well, let's be careful about our sign conventions, minus 3.834. Actually, it's a minus bending moment. Now this is pound feet, so I have to multiply that by 12 inches in a foot. C, well, it doesn't really matter. Let's look at it at this section, so it's the positive C, so that's 1.5 inches. And then the I is 3.27 inches to the fourth. Okay, so we cancel out. Got inches squared over inches to the fourth, so I get inches to the squared below, or a PSI. So we get 3.834, 12 times, 1.5 times. Swap, divide, and then it's going to be a positive. So this becomes positive 21.1 KPSI or KS. I don't know. Your book calls KPSI. I'm used to seeing it as KSI. Okay? 1,000 PSI. That's the stress. All right? So on this top part, it's in tension. On the bottom part, it's going to be equal and opposite. It's going to be compressional stress. So basically, the max stress you're going to have here is going to be as follows. This is at point D. Here you're going to have 21.1 KSI tension, and then down here you're going to have minus 21.1 KSI compression. Okay, and those are the maximum stresses.